everyone. I'm Jean-Noël from Stuttgart, and my role is to assist scientists in doing simulations with energy materials. We are particularly interested in supercapacitors, a device used to store and release energy in large amounts. And even though the term is quite broad and encompasses multiple designs, we have a specific focus on nanoporous supercapacitors like the one displayed here. In this image, what you see is two electrodes, or rather nanopores, represented as a mesh, which are filled with some ionic liquid. And these two electrodes can communicate through the bulk solution at the center. When you apply an electric field, particles with the same charge will be driven out of the slit pores and will reach the bulk solution, whereas particles with opposite charge will rush into the nanopore. In this case, each particle represents actually a molecule, and the blue and red color represent the charge. One of the peculiar applications of these is when you want to store a large amount of energy. Counterintuitively, it's not a good idea to apply a large voltage difference between two electrodes. In fact, if you apply a voltage sweep, you are allowing particles which are trapped in the bottom of the pores to move all the way through the pore into the solution. And so if you charge the capacitor more slowly, you will actually reach full capacity much more quickly than if you applied a large potential difference at the first step. And these devices can find many applications, one of which is to supplement lithium-ion batteries in motor vehicles. If you want to accelerate, you need to deliver a lot of power. And lithium-ion batteries are limited in the rate at which they release energy because they have to remain safe to use. And supercapacitors like the one displayed here are able to deliver a lot of power. Likewise, when you brake and want to recover the energy from braking using some magnetic dynamo effect, you are generating a lot of current and you need to absorb this somewhere. And again, lithium-ion batteries are not great at absorbing a lot of energy very rapidly, but a capacitor like this one can do that. So you can find these applications in tandem with lithium-ion batteries. You can also find them in applications where you have very small devices with a very small battery, but you need to deliver a burst of energy in a short amount of time. You might be wondering why we are using these spheres instead of all-atom systems. The reason is speed. We would like to model very large batteries, which are not ideal. They have small defects in their manufacturing process, and we would like to accumulate very good statistics. And the only way to do that is to actually have a very, very large system. At this stage, we can no longer afford to calculate quantum mechanical effects. We have to sacrifice this accuracy in the name of speed. And using particles like spheres is very efficient in doing this. And this technique is called coarse graining. That's when you use spheres to represent collections of atoms, and you can select the level of accuracy. In the image on the left, you can see some ionic liquid where the user decided to use 4 beads to represent the two molecules, whereas on the right, only 2 beads were used, 1 bead per molecule. In this kind of system, you will have multiple forces at play that you have to resolve. You will typically have some external force, like an applied electric field. You will have a linear Jones force, which is used to prevent particles from colliding into one another and overlapping. And you have a Coulomb force, which is there to represent the electric forces between particles of different charges. And the latter one is the issue. The Coulomb force is long range. So you cannot use tricks like in the linear Jones case. In linear Jones, you have the central particle, and you can calculate pairwise directions between all neighbors in a sphere. And you can control the radius and say, at some point, I will truncate the potential. You can't do that with Coulomb forces. They are long range. If you cut them off anywhere, you will observe very large numerical artifacts. So we have to use another technique to model this. And typically, you will use periodic boundary conditions, where you use the central unit cell and you duplicate it indefinitely in all directions. They actually extend indefinitely in all directions, but for the slide, I cut it off somewhere. When you have such a repetitive motif, you can actually treat the long-range direction as an electric wave because of the periodic nature of the potential. And you can actually represent this wave on a lattice, a 3D grid, where every point on the grid will contain the average of the particle charges in the area. So now you have a way to represent the forces at two scales. You have a very short range, like an explicit summation of all pairwise potentials up to a radius that you choose. And beyond this radius, you will no longer count particle-particle interaction, but instead particle lattice interactions. So you have this explicit sum and the Fourier sum, and you can solve both with a very high accuracy. And the scaling behavior is different. For the short-range part, you scale linearly the number of particles, and the long-range part scales with the n log n behavior. And you use both in the same simulation. Things become a lot more interesting when you have capacitor systems, because here you would like to have something called a 2D plus H periodicity. 2D periodicity indefinitely in both directions, but the third direction, you only have like a small thickness H. And here you will use again a 3D solver, but now the 3D solver is also counting periodic images on the left and right. So you have these slabs repeating indefinitely along the Z direction, and these do not exist in the physical world. Like this is an artifact of how you calculate the 3D Fourier transform. And so you have to correct for this by treating these slabs, which do not actually exist, as infinite lattices with a surface charge. And this approximation is all right when the gap between the slabs is big enough. And this correction scales linearly with the number of particles, and this introduces an extra calculation in the overall simulation. Now, this gap between slabs, you have to define the material inside. You can say, okay, I have some conductive material like an electrode. So we have metallic boundary conditions, and we can now apply some constant potential across the gap. This is interesting when you want to model the charging or discharging behavior of a capacitor. You can also say this gap contains an insulator. In this case, you have some electric material and it will react to the bulk solution of ionic liquid by forming surface charges, because all the molecules in the insulator will try to reorient themselves to minimize energy based on the charges in the bulk solution. And you can treat both with the same algorithm, but then if you have a curved boundary, you have to use another algorithm called ICC star, which will allow you to treat like curves and slit nanopores. All of these algorithms are already available in ESPResSo, and they are routinely used to model electrode systems, capacitors. The issue is they don't scale well on supercomputers, such as the one available through the EuroHPC joint undertaking. And this is where I step in. I am trying to address these scalability issues by reducing the amount of communications between cores. Here is a plot of a simulation of a bulk solution of ionic liquid. The black line is the ideal behavior we would expect the algorithms we use, in this case P3M, to scale with n log n. And indeed, if you use a single CPU core, plus a curve in orange, we are spot on the ideal curve. But you can see at some point around 10 to the power 5 particles, the curve stops because we have exhausted the entire memory of a single computer. This is the reason why we need to have access to these EuroHPC systems. We need to have supercomputers where many computers are connected together with a very high bandwidth interconnect, such that we can simulate extremely large systems with billions of particles or even more. The goal is to simulate systems at the nanoscale up to microscale. The blue curve represents parallel simulations where different nodes in a supercomputer will communicate with one another. And as you can see, we deviate from the ideal n-log n scaling behavior because now we have to communicate a lot of data, not just particles, but also the lattice. Particles, you only need to communicate what's in your neighborhood, but the lattice has to be known fully. But the lattice will not fit into a single computer memory. So each computer, each CPU core has access to a slab of the entire system and has to communicate its outermost layers, but also the local grid. And this has to go through an all-to-all communication pattern, or a bit more complicated than that, because you also have matrix transposes and Fourier transforms in the mix, and these will require multiple communication steps. And this is very expensive, and we need to alleviate this by finding more scalable algorithms. This is a work in progress carried out in collaboration with the ULISH partners. We see three main ways we can solve this issue. The first one, we could tune the parameters of the p-frame algorithm, the one we used for the 3D solver, to spend more time in real space. Again, we have this central particle, and we are looking at all pairwise interactions into a small specific radius, and we can decide to increase the radius. This way, we can now afford to use less grid points in the lattice particle interactions. This means we can spend less time communicating data between the nodes. And here is a trade-off. We are trading off the frequency of the CPU to calculate the to calculate the short-range interactions versus the bandwidth of the interconnect. And depending on the hardware you have access to, how much you can offload between the lattice and the real space is something you have to tune. The next step we can act upon is leveraging shared memory parallelism. We use in ESPResSo a pure MPI implementation. That is, when two CPU cores are next to each other and share the same memory, we are still communicating a buffer between them, which is wasteful. There are P3M libraries available that actually use OpenMP parallelism to actually share data and avoid these extraneous communications. You actually only need to communicate between two CPUs. And this is something we are actively working on with ULISH to integrate into ESPResSo. And the third aspect is offloading. With libraries such as Cocos, you can decide to offload specific algorithms to vectorized CPUs or GPUs. And this will again depend on which hardware you are using. Some EuroHPC systems have a mix of CPU and GPUs, and others have like very modern CPUs with very large vectorized registers. And here, Cocos will be able to tune and decide which offloading or which hardware is best suited to a specific algorithm. As a multiscale partner, my goal is to offer well-scaling solutions to model large systems of energy materials, and we would like to make these algorithms available in Scafacos, like a self-contained library, which you can reuse into other softwares. The goal being that other softwares available in the market can reuse the tools we are developing to accelerate their own applications. And we are using ESPResSo as the framework to develop these algorithms because it is extremely flexible and it is routinely used by HPC users to simulate large systems and clusters. It is available on EasyBuild and EESSI, which means when we rapidly prototype new algorithms, we can, in between releases, stream like release candidates on EESSI and make these available to our community, and then they can tell us their feedback, whether this is better or worse than the previous release candidate. And then we can very rapidly test and deploy our software without having to ask our users to compile ESPResSo with the new code from a commit and to select the correct dependencies from OpenMPI, RMPish, and so on. Everything is streamlined with EESSI. I would like to give a shout out to all my collaboration partners and also thank you all for your attention.
Okay, thank you, Jean-Noël. Before we continue, I would just like to remind you that you can post your questions through this Q&A button in your Zoom portal. And after the next talk, we will have this Q&A session. So the next speaker is Alan Okesh from University of Barcelona. And he will tell us about the easy CI/CD services for ESPResSo and PyMB. Alan, floor is yours.